Hello, welcome back to the third lecture of week 5. So we will continue our discussions on transformer architecture, and in this lecture we will try to complete the discussion on the encoder part. So these are topics that we will cover in this lecture. So we'll talk about one missing link that we have not talked about in the encoder, that is the positional encodings. We'll briefly discuss about the matrix calculation of self-attention part, and then we will also say how this method is very generic and can be applied to other modalities also. So we will see briefly how you can use this transformer architecture to also encode images. So let us go back to our transformer block that we had discussed in the last lecture. So we talked about this, that what you will do. So suppose you have a sequence of words. So first of all, as we had discussed in the very early lectures, what you will do the byte pair encoding based tokenization of the sequence, and you will, let's say these are the tokens that you get. It can also be subwords. So they can also be subwords. Now how do you feed these subwords? You have to feed these via their embeddings. Now it may happen that you have already learned these embeddings separately, or you want to learn them together. So in the transformer paper, what was done, the embeddings were also learned. So you also learn the embeddings. So what does that mean? So each word is fed as a one hot vector. So suppose your subword vocabulary is 50K. So you have 50K dimension one hot vector. So each word would be somewhere in the one hot. Let's say the occurs here, and then you have an embedding matrix, right? So you will multiply it with an embedding matrix. So this can be 50K times whatever the final dimension you need. In this case, I need 512 dimension, the model dimension. So I'll have 50K into 512, that many parameters in the embedding matrix. And this will also be trained with the model, assuming you have sufficient data for training this. And once it is trained, this is your embedding, right? So then, given a word, you will directly apply one hot to this matrix and you will get the embedding. So this is what happens in between. So you are multiplying with the embedding matrix. Depending on whether you have already learned it or not, you will also train those parameters. So now you have got the input to the first encoder. After you get the input, you apply multi-head self-attention that we had described elaborately in the last lecture. So after multi-head self-attention, you will get a final output. Then I apply some tricks to ensure that my training works well. So I add this input back as a residual connection or skip connection, and because I am keeping on adding, my input keeps on getting shifted, I do layer normalization. So this add and normalization block is very crucial to the transformer. So once I have that, this is my self-attention output, you can say, after add and normalization block. And this is the input to the next thing that I will do, feed forward neural network. So I'll apply feed forward neural network, I can get an output and repeat add and normalization. So add it back and do normalization. So I do that. So this is what we have discussed about transformer block. You keep on doing that on multiple encoders. So you have this one encoder, you apply this output will go as an input to the next encoder, and so on. In the original paper, they had 6 such encoders. Okay. So now, is this the complete picture of encoder? Now there is something missing still, right? So what is that is still missing in this encoder? So can you spot one major problem here? The major problem is that I am getting some output. So I am feeding some words here, W1, W2, and so on, and I get some final representation, right? And this looks like RNN in one sense, that you are getting a representation of the input sequence, and you can do whatever you want. You can do sequence labeling, you can do classification, right, with this. Okay. But what is missing? The missing point is, it doesn't care about the word ordering. So this word will give this representation even if it was at this position, it will still give the same representation. So the representation of a word will not depend on the position where it is. Now this may be helpful for some languages which are like free word order. Language like Sanskrit, if you are dealing with poetry, so we have seen if you can just feed it like a set of words and this should still be fine. But language like English that are typically written from left to right, the order matters for them, right? So how do you know whether, so the difference between cat kills dog and dog kills cat, right? So the order tells me who is the subject, what is the object here. So order is important for language like English. So how do I encode this order information in this? So that is the major thing. So right now the order does not matter in the transformer encoder the way we have described till now. So how do I incorporate the order information, that this is the first word in the sequence, second word, or that these two words have a distance of 1 and 2 and so on. So what we do, so we add some position embeddings to the word embedding that we are learning. So suppose these are the word embeddings for the words. So we add some position information to that and we pass it before the first encoder, so that we have some information that this word is in the first position, second position and so on, right. So we add some quantity to each input embedding unit, and this dimension will be same. So my embedding is 512 dimension, this will also be 512 dimension, and it will depend on the absolute position of the input. That means let us say I have a maximum length sequence. So in this case transformer, this was 512. So I can encode 512 inputs, 512 words, and each word can have 512 dimension. So I need to know all these 512 cross 512 parameters for position embeddings, for position encoding. So what do I do with these parameters, right? So what are the ways in which I can fix these parameters that give me some position encodings? I'll add it, and then I don't have to worry about the order information. This will take care. So there are many ways of doing that. In the original transformer paper, they introduced something that are like absolute numbers that are not trainable. So you just fix the position encoding by some interesting method, and the method was actually very interesting. That is, okay, what you do, you use sine functions of various magnitudes, okay, various periods. So for example, so what you are seeing, so you see we have two different things. So we have 512 cross 512. So one is the position, second is the dimension. So one is the position and second is the dimension. So each position 0 has 512 dimension, position 1 has 512 dimension, and position whatever I has 512 dimension. Each position has 512 dimension. So first of all, how do I fix for each position and how do I do for each dimension? So what they did, so for each dimension, so think about now the first dimension for all the positions, first dimension of all the position. What they will do, they will take a single sine wave. So here let us say, so this is told for dimension 4. So the blue curve is for dimension 4. So let us go to dimension 4. So this blue curve will tell me what is the dimension 4 at each position. So how will I vary the position? It's a sine wave, so it will have some various values at different point. So I'll simply take, for example, position 0, this is the value, position 1, this is the value. I mean just saying, but we will take a look at the exact formula. Position 2, this is the value, at position 20, this is the value, right. So I have a value that I can put each position for the fourth dimension. So this is only telling me the fourth dimension, okay. And you see this will gradually change. So that's what we want. When we go from position 1 to 2, there should be some gradual change, and as you go from 2 to 3, again some gradual change, and that's what will happen. As I keep on progressing a position, there will be some gradual change in the value of this. And same, this is for dimension 4. If you want to see as dimension 5, I have another curve, right. So this was sine wave, this is cosine wave, right. Cosine of 0 is 1, cosine wave. So again I will see, okay, what is the fifth dimension value for the zeroth position? I will take 1. What is the fifth dimension position for the fifth dimension value for the first position? Yes, I will take what is the corresponding value of this curve. So that is the interesting way in which all the 512 cross 512 values can be found. Okay. And so they use alternatively sine and cosine, right? For the first, say for the geo dimension, they'll use sine, next dimension cosine, and so on. So alternatively sine and cosine waves. Okay. So to look at the exact formulation, so what you will do, suppose you have the kth word, right? So kth position in the sequence. So what I will do, I have now d dimension to fulfill. Okay. For the kth position, d is equal to 512 dimension. So what I will do, so I have two different waves. So I have for the kth word, I have dimensions. I will alternatively use for each dimension sine and cosine. So even position, 0 position, I will use sine, and odd position, I will use cosine, and so on, right? And what is the value? So this was the function sine of k is the position, divided by n to the power 2I by d. Right? This will vary the period of the sine wave. So what is so this is the position function. So you have 2I and 2I plus 1. So you do alternatively sine and cosine, and then again you will do 2I plus 1. So that will go to the so position 0, I is equal to 0, and I is equal to 1 will give you position 2. Right? And if you do I is equal to 1 here, it will give you position 3. Right? So you will do 0, 1, 2, 3, 4, 5 with sine cosine waves. And n is some scalar that is user defined. So they took 10,000 in this case, and you understand d is 512, and I, as you can understand, will go from 0 to up to d by 2. Right? It will go up to that, so that finally you have n to the power 1. So that will be the largest sine wave. Right? So just to give a toy example, so let's say we take very small values. So n is 100. So this was actually 10,000 in practice, and d is 4. It was 512 in the paper, and you want to find out the cosine, the actual position encoding. So let's say, so for 4 position, so 0th position, first position, second position, third position, I am a robot. So at the 0th position, I have to fix these 4 dimensions, right? They are 5 and 2. So how will I fix the first the 0th dimension, this dimension? So this is, I will take k is equal to 0, and this is even. So I will take this function. So I will take sine of k 0, 0 by something, n to the power 0 will be 1. So this will be 0, sine of 0 is 0, right? So for the first dimension, I mean the next one, I will use this one. So cos of 0 by something, so this will give me 0, this will give me 1. So I have fixed as 1. Next again, I mean the k is 0, so this will remain as 0. So this will remain as 0 for all the even position, and this will remain 1 for all the odd position. I mean, you can see this is starting from index 0. So this is why this is even, this is odd. Next one, fine. Now k is equal to 1. So I is equal to 0. I will take the sine 1. Sine of 1 divided by k is equal to 1. N to the power n is 100 to the power I is 0. So this is again 1. So sine of 1, and sine of 1 becomes 0.84. Right. Similarly, this will be cosine of 1. Next, for I is equal to 1, this will become sine of 1 upon 10 to the 100 upon 100 to the power 2I by d. So 2 by 4, d is 4. So 1 upon 100 to the power half, that is 10, 1 upon 10. So this is sine of 1 upon 10, that comes out to be 0.1, and cosine of 1 upon 10 comes out to be approximately 1. Right. So that's how you can fill your positional embedding. And if you see that, so there is a gradual change in this dimension, right? 1, 0.98, 0.96, and as you keep on increasing, so this change becomes more gradual. Right? So that is the idea of positional encoding. Now this is an absolute position encoding and not learnable. So you fix it, and you can just retrieve at runtime. I mean, whenever training or inference time, you have the embedding, you add the position encoding from a lookup table, and just feed it to the transformer encoder. We will do the same for decoder also. So, but there are other ways, right? So one can say, okay, why can't I learn this position encoding also? Yes, you can. So you can also learn this position encoding. So what you will do? So let's say I want to learn a position and embedding matrix, right? So what does that mean? I have to have position encoding for each position. So, suppose they are in position, and each position you have the same 512 dimension or the model dimension for each position from position 1 to n. You have to learn this. So, what I will do, so I will just initialize with some randomly initialized embedding and one for each integer, right, up to some maximum length. So, here, so this 1 cross n corresponds to one particular position, and then you will have whatever number of positions you want. So, what you will do, for example, the word fish, if it is at token 3, position 3 versus position 17, we will have separate embedding for position 3 and 17, right, and you will learn them starting from random initialization. You will train the model to learn what is the optimal position encodings. So, this is also possible, and this is also done in various later works. So, you do not fix them as sine and cosine, but you can also learn these. So, in practice, later on various different works have used multiple ways of doing position encodings. So, for example, so we talked about learned position embeddings, so that were used in various models. So, PERT, GPT and all, they used learned position encodings. So, sinusoidal embeddings we talked about in the original transformer paper, but there were various later papers that said, okay, what we need is that relative difference between tokens. So, there were works on relative position encodings and relative positional bias, right. Different works we did that, like D5 had used a different position encodings. And then one recent trend is to use rotatory position encoding. So, rope. So, in very recent models like Llama, Gamma and all, they use this rotatory position encodings. Now, we will talk about the exact formulation of these at later point in this course, but for the idea is that yes, there are various ways in which people have tried to do position encodings for the transformer model. Now, let us talk about some more details about self-attention, specifically what is the matrix formulation of this. So, with a simple example, let us say we have this input thinking machines. What you would do first, I will get the embedding, right. You can think about adding the position encoding also, and using these three matrices WQ, WK, WB, I will get the query key and value for all. So, just to give one example, suppose what you are trying to do self-attention weights for thinking. So, I will take the query from here and key from both the words. So, Q1.K1, Q1.K2 you will compute. So, right now you see the numbers are quite large, right, that is why. And while we talked about the reason for skill dot product, this is to maintain mean 0, variance 1, but you see it has another impact on the final computation. See, you can relate it to somehow scaling these logits, right. So, suppose you have just 112 and 96, and I want to get the attention distribution. What will be that? It will be e to the power 112 e to the 96 divided by the summation of that, and you see it will be roughly. So, this is e to the power 16 divided by e to the power 16 plus 1, and 1 divided by e to the power 16 plus 1. So, e to the 16 is such a large number that this will be roughly like 0.99 something, and this will be another which 0.0001. So, the word that has a larger score would have the entire impact, and other words will not even feature. So, you want to flatten the distribution a bit, and that is what happens by dividing a parameter. So, we talked about temperature, we divide a parameter that is less than 1. So, what happens? So, the distribution becomes sharpened, but if you divide by a parameter greater than 1, the distribution becomes flattened, right. So, this typically flattens the distribution. So, that is another impact that it has. And then you divide by 8. So, 64 square root is 8. 14 and 12, now it is reasonable, e to the power 2 upon e to the power 2 plus 1, 1 upon e to the 2 plus 1, and this is reasonable. A square is roughly like 8, between 8 and 9. So, this is reasonable, both will have some value, right, some reasonable value. So, this is another interesting part about scaling of dot product for attention. Now, you can, we said you can do all these operations in parallel. How? So, you have two words, and each word has an embedding. You can put that as a matrix. So, X is a matrix that denotes the embedding for all the words in the sequence. And now, you have these 3 matrices, query, key and value. So, you multiply this entire matrix with this, you get the query matrix, key matrix and value matrix for all the words in the sequence. And now to get the attention output for the entire sequence, what you can do, you take all the queries together and multiply by the key transpose. And then you can also do square root of decay scaling here and then multiply by the final value vector. And this together will give you the attention output. Right? You can see this has the same effect of doing it individually. So, now you are doing it for the entire set of words, right, by multiplying. So, each word you will do for one row, you will multiply by keys and all the values, but now you are doing it in parallel for all the words in the sequence. And this gives you the self-attention output for all the words. Now, this is for one head. Okay. So, this is what you are doing for one head. So, this is your Q0, K0 and V0 for the attention head 0, and you are multiplying this whole matrix and getting the output from the attention head 1. But next you can have next attention head Q1, K1, V1 and same process, but different matrices. Okay. So, you can do this for all the heads whatever we described in the previous slide. Okay. And you will get the outputs from each head. So, suppose there are 8 heads. So, G0 to G7 are the 8 outputs. You will now concatenate these and multiply by another matrix W0. Okay. So, this would be multiplied by another matrix W0 and the result will be a matrix G that captures information from all the attention heads, and this is what you will forward it for everything else like add a normalization, feed forward layer and so on. Right. So, this was your H times TV matrix and this WO will take H times TV back to D dimension. In the paper actually they had the same dimension. So, H was 8 and DV was 64. So, this was already 512. So, you go from 512 to 512 again. Okay. And then this is the whole process. So, your input sentence, you embed all the words in a matrix. Now, in the later layers in the encoder, so you can think about the output from the previous layer as getting here, but it will have the same dimension. And then you have attention heads, multiple attention heads, different query key and value. Use that to compute the matrices for query key and value for each attention head, get the output from each attention head and then multiply the concatenation of this with W0 to get the final self-attention output. Okay. And this is what is used later on, whether you want to do add a normalization or you want to do feed forward network, and this will be common for all the layers. Now, this is how you can see one encoder block. Right. So, you have embeddings, positional encoding, you add it, you get the input to the encoder, self-attention output through the entire process we discussed, layer normalization. So, add a normalize x plus g to layer normalization, add a normalized block, output of this do feed forward, again do this add a normalized block, and this is the output for the encoder 1. And similarly, you will have other encoders. Now, let us try to find out what is the number of parameters that you have in the encoder. Right. So, how many parameters are there? So, let us leave out the embedding parameters. So, you will have embedding parameters also if you are training these. Some if 50k is the vocabulary times the model dimension. So, V cross D will be the number of parameters that you need for the embedding. Let us see how many parameters you need for your encoder block. So, encoder block has self-attention and feed forward. Right. So, let us see the number of parameters for self-attention, then we will see for feed forward. So, how many parameters you need for self-attention? So, in self-attention block, what are you doing? So, you have, let us say, H number of heads, and typically the way you do it, so you have D is the model dimension that you want to maintain, and generally what you do, your dimension for query, key and value are all same, that is kept to D by H, right, and you have H heads. Okay. So, what are your 3 matrices WQ, WK and WV? They would be D times D cross H, each of these, right, into 3 such matrices. Now, you have 3 such matrices for one attention head. So, So you will have similar matrices for all the H attention heads. So you multiply by H. So this is for multi-head attention, right? And this comes out to be 3D square plus the output, that is H times dimension of K, that is D by H. This you project back to D dimension by using WO matrix. So this will be H times D by H, D times T. So this is also D cross D. Okay. So that means 3D square plus D square. So you have 4D square parameters for your self attention. Great. Now what next? Next you have a feed forward layer. So how many parameters of feed forward? Feed forward we talked about. You will take the output from the previous layer, T dimension. You have a hidden layer of 4D dimension and put it back to D dimension. So you have D cross 4D and 4D cross D. So 4D square here, 4D square here. So 8D square parameters in the feed forward layer. So you have 4D square self attention plus 8D square in feed forward network. So together you have 12D square parameters in one encoder layer. And if you have L layers, so you multiply it by L. So if you work it out for transformer encoder, so D was 512 and they had 6 encoder layers. So you will get 12 times 512 square times 6. Now 512 square, roughly you can say this is 25 0000 into 12. This becomes 3 million roughly into 6. So roughly 18 million parameters in just the encoders, right? So encoders had roughly 18 million parameters based on their corresponding model dimension, and this would change if you change your model dimension. So this does not include the parameters for the embedding matrix. Right? So 18 million parameters, right? So this is a huge number of parameters that you can see in the encoder itself. Great. Now, so in this lecture, I also wanted to discuss that transformers are a very general sort of mechanism by which you can give any set of representations and can learn how to encode that. So we talked about how to encode the text, but what about images? So let's say I'm given an image, right? So how do I encode using transformer? Idea is if you can give me some x1 to xn representations, latent representations, say the model dimension, I can just use the exact encoding framework to encode and obtain the final h1 to hn representation. Right? I can do that by transformer. The question is, how do you get this representation from image? And the idea was very interesting. So this ICLR 2021 paper, that introduced vision transformer, it said, okay, what you can do, you have the image, just create patches out of that, so of similar sizes, and each patch, now you can think of this patch as your sequence. So you can take some ordering of patches, patch as your sequence, and you learn how to project it to some latent dimension and add some position encoding, and this you will feed it to the transformer. Right? This was not very difficult task. So once this was conceptualized, it was not very difficult task. So you have to learn how to take a patch and convert it to an model dimension embedding, right? Add position encoding and just feed it to the entire transformer encoder. Right? Now what would they do little bit differently, because the objective was different. So they had the image in a data set where each image had a class. So what they did for training this model, so they introduced another token, that is the CLS token. So this is an idea that okay, I can put another token whose embedding, so embedding of CLS token will tell me everything about the sentence. It's like the sentence representation. Right? We talked about this in the case of RNNs, where the final state was sentence representation. Here you can use an explicit token which is supposed to capture the entire representation of the object, in this case the entire image. Right? So because by self-attention will attend to all the words or all the patches in the sequence, it is trained such that this will do the classification finally, that whether it is a bird or car or something else. Right? So idea is very simple. You have an extra trainable embedding, and this will anyway attend to the entire patch. So its representation finally should capture what is the class. And that's how it is trained. Now, what do you need to train this model, right? So little bit of idea. Let's say your image is fixed to h cross w is the dimension, height and width, and c is the number of channels. So say RGB channels. You can say c is equal to 3. What you will do, you will create patches out of this image. So we will create patch of some dimensions, let's say p cross p. So this was 16 cross 16 in this paper. So let's say p cross p patch. So how many patches you will create? So you have h cross d image, h cross w image. You create p cross p patches. How many patches? H w divided by p square. And let's say you get this is equal to n, right? And this becomes your effective sequence length. So you will have now n patches, each of p cross p. Done. So you have been able to represent image as a sequence of patches. Now next thing is, how do I encode them as latent representation? Right? Like words one hot to embedding. Similarly, now I have to do from patch to embedding. Right? So each patch is p cross p, and it has c channels. Right? And they are all some values between 0 to 255. Right? So what I will do, I will learn how to project it to some model dimension. So this p cross c will be projected to d dimension, which is very easy. I learn a matrix that is p square c times d. I learn this matrix to project each patch to d dimension, right? And done. So now my transformer only sees these d dimensions. So this is the model dimension, right? And it can do its whole machinery on this. So self attention, feed forward, everything till the top. And because you also want to encode position, I'll just add n plus 1 times the learnable position embeddings. Because why n plus 1? Because n is the sequence length, plus you are adding a CLS token in the beginning to denote what is the class of this image, right? This will be very, very crucial for us. Later on when we talk about BERT, we will again come back to the CLS token. But the idea is that you have giving a functionality through which a single embedding can represent the entire sequence. Otherwise, you will have an embedding for each word independently, and you can use some mean or summation of those embeddings to get the sentence representation. So, okay, so the parameters I need at the embedding are this and learnable position encodings, n plus 1 times d, and that's all. So, and then you have the entire transformer parameters, and you can learn how to encode images. Okay. So this completes our discussion on the transformer encoders. Now, how do you connect the decoder? So we started with transformer encoder decoder. So how do you connect the decoder with that is what we will see in the next lecture. So you can go through this chapter 9 of the book to continue reading about transformers.